Is I audible for you? Good morning. Is I'm audible for you? Please reply me, guys. Screen is shareable at your end.
Yes, sir.
Yeah. Okay. Let's now we start the discussion. Last lectures we are discuss about the what are the current components in the diode in the PN junction diode. So we will take a slightly review of that one, and then we will go for the derivation of a diode current, derivation of a diode current in a PN junction diode. So lastly, we have seen that if we consider that this is a PN junction diode is connected as in a forward bias configuration, then there will be a number of components are associated with each other. So what are our components are in the p-type material as well as in the n-type of material. We are familiar that in the p-type material there are majorities are the holes and minority carriers are the electrons. Whereas n-type of material we have majority carriers are the electrons and the minority carriers are the holes. So what is happen if before a voltage is applied, yes, there is a recombination between majority electrons from P region to the N region. So, sorry, majority electrons from N region to the P region. So as there is a recombination takes place, they will be diffused near to the junction and the diffusion layer is formed. Okay. So this is one of the component is formed. Similarly, here from the P side, here we have majority carriers are the holes that will also move to the here. Yes, so therefore there will recombination will be takes place, and as their recombination will takes place, yes, or there will be a current will be flows, current component will flow from a holes from a P side to the N side. Yes, this is the movement of electron. What is the conventional current? Conventional current direction is from a left side to the right side, and from considering the electrons, it's a again from a conventional direction is a from a left side to the right side. So these are the two current components associated with this. What are that? If we consider that here these p-type material and n-type materials are joined, there is a deflection layer is formed, and once they form a deflection layer, their holes are crossing to the junction into the n region, and they recombine, and then they will be create here a minority carriers in the p region. Similarly, the electrons which are crossing from a N region to the P region, they will be recombined and they will be stay in the P region and behave as a minority carriers. So finally we can say that here the current component here it is due to the minority carriers. So we have the current at one current component in the P region, which is a minority carrier from the electrons, so the electrons which are coming from an N region. So let's that we will represent it as a electrons from a N region, and similarly the holes are crossing here, and once it is crossing here, they will behave as a minority carrier in the N region. So what is the minority carrier in N region? It's a, we will represent it as Hn. Yes, and minority carriers here it is a from a P, N side is what? it's a E end. So lastly, we are represented that these two parameters component associated with this one. So finally, as this is a PN junction diode is a series connection network, so the current due to the minority carriers in the N regions and the current component due to the minority carriers in the P regions will be same or it will be additive manner. So the total current at this point is a constant, and so therefore it is given as addition of these two components. Here you have minority electrons, which is represented as here this one, okay, first parameter, and here it is you have minority holes which are represented by these parameters. So since this circuit is a series circuit, so at the same time these electrons are moving from a N side to the P side, and the actual conventional current is from a P side to N side. Whereas for the hole, it will be again from a P side to the N side. So in the both the situation, if we consider that the movement of electrons from left to right and the electrons movement is from right to left, and a conventional current direction is for holes is left to right, and for electrons is again left to right. So the same direction, so current will be additive, so it will be represented as like this. Now what will be happen if here we are discuss about electrons, sorry, holes are crossing here in the end region and they behave as a minority carriers, and due to that component is there. Now if their external voltage is applied to this PN junction diode, then we will have here a majority carriers are the what? Holes, and here it is you will have the majority carrier in N regions are the electrons. Now, once the barrier potential is break by the external voltage, then this majority carriers from the P region and holes and from electrons from N region will be combined. Okay, and this process is by the external force, which is called as a drift phenomenon, or it will be external forces applied. So therefore that the majority carriers will be moved from a P region to the N region. Similarly, majority carriers from a electrons is also moved from a N region to the P region. So finally we can say that here again for here again two more components are associated with this PN junction diode due to the majority carrier. Why this majority carrier will move? Because of external forces are applied. So that there will be a drift phenomena will be takes place. What is mean by drift? Drift means with the displacement of a movement of a carriers from one point to the another point by the applying external force. So therefore, again we can say that here again there are two components associated with the PN junction diode due to the majority carriers. So finally, we have a total four components associated with this PN junction diode. One is by the diffusion process and one is by the drift phenomenon. So the by the diffusion process, we have the minority carriers. The minority carriers in the P regions are the yes electrons, and in the N region are the holes that will be constitute a one current, and by the external force drift phenomena is takes place. The majority carriers from the P side and the majority carriers from the N side electrons will be also there. So finally we have here the for majority carriers the current compound, sorry, majority carriers will be moved from left, holes carriers will be moved from left to right. At the same time, the electrons, majority electrons from the N side is also moved from a right to left. But as a electrons moves from the right to left, the conventional current direction is exactly opposite. So therefore, again you will have here conventional current direction due to the holes is from left to right, and again from here for electrons will be again left to right. So finally we can say that here are four components are associated with a PN junction diode, which are represented by this way. So here the first component is due to the diffusion process. What is the diffusion process? When before applying external force, there is a recombination takes place between here holes and to the ends, holes and the electrons in N region. Once the holes are enter into the N region, they behave as a minority carriers. So the minority carriers in the P region, sorry, minority carriers in N region is represented as a like this way. Minority carriers in a P region due to the holes, yes, it is a represented exponentially like this way. Okay, this one part. Similarly, we can write for the N components, electrons are crossing to these junctions and they behave as a minority carriers. Now that minority carriers by the diffusion process is represented by blue line. Now if we apply external force, then there will be a drift phenomenon as it takes place. Then majority carriers are to be flows from here P side to the N side. So what is the majority carrier in the P side? Majority carrier in the P sides are the holes. What about the majority carrier in the N side? In the N side, majority carriers are the electrons. So from these graphs are shown like this way. It is seen that, yes, guys, it's a seen that here all these exponential gradients are decreasing it. Why it is a decreasing it? Because we know that the current density, yes, is given as a charge into the density constant into the density gradient, and this density gradient is exponentially decaying. So this is a current component associated with the junction diode. Now guys, we want to go for next is a quantitative theory of a PN junction diode current. So for quantitative theory of a PN junction diode current, we have to concentrate that the what is a electron hole, what is the concentration component for the n-type material. So let's, if we consider that when a PN junction diode is formed, then what a PN junction diode is formed and it is used in forward bias, what is the current in that case equation, as well as when the PN junction diode is connected in the reverse bias, what is the current in that situation? These two we need to find. And for that purpose, let's see if we consider that when a PN junction diode is a forward bias, yes guys, what we will have? The holes are injected from the P region to the into the N region. The concentration of holes in the N region is above, the concentration of holes in the N region is above the above the thermal equilibrium value. Let's the thermal equilibrium value is represented as a P and O. This is a, we will have the concentration constant. This is by the semiconductor theory. It is given as an exponential expression and which is exponentially decaying. So what is the whole concentration at the in the N-type material? What is the whole concentration similarly for a P-type material? Similarly for a P-type, the same cause. Yes, again only the change is there in spite of holes. Sorry, in spite of holes, there will be electrons due to the minority pairs. So let's see if we decide the concentration of holes in N region, thermal equilibrium value P and O is given as, guys, yes, this is the expression. If you observe that this is exponentially decaying, these are the what in the N type of materials, excess electrons are entering into the N region from a P region and they will behave as a minority carriers. So these are the excess are entering into the at the edge of the junction once the crossing the junction. So these are the minority, these are the carriers are the present, which we will call as a injected carriers or which we will call as also excess carriers are there. So what is that expression? So therefore, if we consider, we have to write the concentration of holes in n region at considering a thermal equilibrium value PnO0, then it can be written as it's an addition of this exponential curve as well as a thermal equilibrium. So you have it's a Pn of x is equal to thermal equilibrium constant plus its a exponential curve by the diffusion constant curve, concentration curve, which is given as a P dash n of a 0 is equal into e raised to minus x divided by LH. What is x? X is a distance from a junction. Yes, where the x is the distance from the junction and h is the diffusion length of the holes in a n-type materials. Now, what is the excess or injected concentration of a hole in the n-type material? So the excess concentration of a holes in the n-type material is this portion, only this portion. So this portion can be given as the subtraction of this portion minus a thermal point, thermal equilibrium point. So it can be given as a Pn dash of a 0 is equal to Pn of a 0 minus Pno. So guys, Pno it's a represent this is a thermal equilibrium point. Okay. So the diffusion hole current in the end region is given by by the semiconductor physics theory. It is given as current density is given as minus A. A is the area of the material, area or cross sectional area of the semiconductor material. E is the charge. D is a diffusion constant, and this is a derivative of a Pn is a gradient constant. We know this one expression. Yes. So we can take a derivative of this expression and we will plug this value in this expression. So what is the derivative of this one with respect to x? So this is a constant. Yes. Only the variable is the exponential. So if we this is a Pn dash is also constant outside. So what is the exponential derivative of exponential? It's a exponential divided by their constant. So according to that expression, this the whole movement in the n region, n type of materials, the whole holes which are present in the n type, which constitute the current, is given as a into E charge of the carriers dH. Yes, it's a diffusion constant which is given as a for the holes, and here it is a P not 0. Yes, exponential this one. What is LH? LH is nothing but a length of a diffusion length of the holes in a N type of a materials. Now continuing with that theory, now what will be happen if at the junction, crossing the junction, here it is what you have? Here it is a, for this side you have the P type materials are there. So definitely here the electrons from the, here it is a crossing it and they behave as a minority carriers. Same discussion will be carried out. So firstly we will complete the discussion about the N-type materials. Here the holes are injected, excess holes are injected in this region. That is it. So at N, at the junction, x is equal to 0. Yes, simply we are plugging x is equal to 0 in the previous expression. We have the AE dH Pn dash of a 0 divided by LH e raised to minus x divided by LH. So simply we will plug x is equal to 0 here. X is equal to 0. So finally you will have this expression which is given as yes guys. Yes. Now what is this expression? This expression can be also written as from a previous expression. Yeah, this one. Okay. This expression can be slightly rearranged. Yes. Pn of x minus Pno of x. So therefore, this expression can be represented as a for this way. So finally, we have this expression where what is a is a area of a material in the meter square. ds is a diffusion constant for the holes, which is given as a meter square per second. E is the magnitude of a charge on the holes. L is the diffusion length of the holes in meters, and the Pn dash of a 0 is the excess of the holes concentration at the junction. So considering using the Boltzmann relationship of a kinetic theory of a gases, this can be given as, yes, this one is a Pn of a 0 is equal to Pno e raised to V divided by Vt. This expression also we have found out in the from a contact potential theory. So that can be given as a. So next, where it is a V is the applied voltage across the junction. Vt is the Thevenin's voltage, Vt is the voltage equivalence of a temperature. What is the voltage equivalence temperature from the contact point theory or a contact expression? Contact potential, which is given as a T divided by 11600. So it's a T divided by 11600 will be a temperature. Yes, and it's a depends on a temperature components. So it is given as a like this way expression. So now here where the LH is there, which is a diffusion length. So we need to define what is a LH. So the diffusion length is defined as a distance traveled by free charge carriers or either electrons or holes before the recombination, and it is given as considering the to cross from one point to the another point, it requires some duration, it requires some lifetime, which is represented as a tau h. So since we are considering excess holes in the n type of a material, so it is given as a LH is equal to under root EH tau h. Yes guys, so you will have this one. So similarly for excess electrons are in the p region, excess electrons, and for that case it can be also given as the Le is equal to under root dE tau E is there. Now what is the forward current at for this case? Okay, so the total current at a distance, yes, at the junction x is equal to 0 is given as a what? The holes in n regions and the electrons in a p regions, which are the excess electrons are there. So Hn is 0 is caused by holes entering into the n region, and IEP of a 0 is caused by electrons entering the p region. So we have this value. Already we have found out the expressions of this one. So what is the expression of the finally we want to find this expression as well as this expression. Once we have this expression, we will have that. So what is this current already we have found? This current already we have found in the previous slide, which is given as AEDH divided by LH Pn of Pno or e raised to V divided by Vt minus Pno. So if we take it this thermal equilibrium constant outside, so you will have the AEDH Pno divided by LH into e raised to V divided by Vt minus 1. So means if you observe that excess holes are in the p type n type of materials are depends on what is the area, what is the material, sorry, cross sectional area, charge, diffusion constant, and the thermal equilibrium point and the diffusion length, as well as what is the applied voltage externally to the PN junction diode and the temperature dependent constant Vt. Now this one we have found out for a Hn of a 0. Similarly, we need to find the excess electrons which are available in the p-type material. So for that case, it can be given as a similarly. Yes, it is given as a, guys, AE. Now due to the electrons, diffusion constant is E, dE subscript E. Yes, equilibrium constant, and the length, diffusion length due to the electrons is Le. So similarly we will have this. So simply we will plug the previous expression and this expression in the additive expression of the battery. So you will have the current I is the, yes, the in this expression. Is the expression is the, like this way, AE, yes, DE NO 0, NPO 0 divided by LE plus AE, yes, DH PNO divided by LH. Guys, E stands for here, E stands for charge carriers are there, into e raised to V divided by Vt minus 1. So let if we consider this constant first square bracket as a one term as a I0. Yes. So finally, where we have, this is a final expression for the PN junction diode, yes, in the forward bias condition. So we have the I is nothing but the diode current under the forward bias is I0 into e raised to V divided by Vt minus 1. Where I0 is which is yes, it's a due to the reverse components, which is depends on all these components: length of electrons, length of holes, diffusion constant associated with electrons associated with holes, equilibrium constant associated with the holes and associated with the electrons, and the area of materials will be there. Now what will be about a reverse diode, reverse saturation current? The concentration of holes in n-type regions and the electrons in a p-type region is given as, yes guys, by the intrinsic theory, which is PNO is equal to Ni square divided by Nb, and NPO is equal to Ni square divided by N. What is a Ni? Ni is the intrinsic concentration. So you will have that. So putting this value in this expression, so we will slightly rearrange this expression as reverse saturation current I0 represented as I0, denoted as I0, is equal to AE DE divided by LE NE plus DH LH VD, taking as Ni is a common. So means finally we can say the reverse saturation current of the diode is depends on intrinsic constant. Again, diffusion constant, length of the electrons and the holes, and donors, here guys is a ND, it's not a VD guys, please kindly check it. This is the ND, yes, it's not a VD, so it's a donor as well as the acceptors are there. So, for intrinsic semiconductor, this Ni square is given by as A naught T raised to 3 e raised to minus E subscript Go divided by Kt. Now, what is here Eg? Eg is nothing but a Fermi level in the energy band diagram. So, from the energy band diagram, this expression is there. So finally, if you observe that intrinsic semiconductor is depends on the area, temperature, and yes, it's a this EGO can be represented as energy can be represented in terms of a voltage. So it's a VGO divided by VT. So it is a K divided by T. So we know that K divided by T KT divided by Q is nothing but we will have the Vt, and so Vt is what? T divided by 11600. So here V0 is a voltage numerically equal to the forbidden energy gap in the electron store. So for a germanium, the diffusion current DH and the DE varies exponentially inversely proportional to the temperature. Hence, I0 is given as this for I0. So this is a constant considered. It's a slightly represent for the silicon for a germanium material. Similar, if you observe that reverse saturation current for the germanium, it depends on a, yes, it depends on a forbidden energy which is in volt, thermal voltage temperature constant, temperature and their constant K. Okay, this K will be here, this one. So this is a K1 is for a germanium. So the PN junction diode can be a silicon material. Yes. So for the silicon diode, this one, yes, all this discussion we have carried out that is the diffusion current is negligible in comparison with transition layer generation. So, yes, so for silicon material, it can be also given as I is equal to reverse saturation current into the e raised to V divided by intrinsic N Vt minus 1. So for the germanium, this intrinsic N is considered as a 1. Okay, whereas for the silicon it is considered as intrinsic N. For depending upon the what type of a current, whether it is a small value of a current or large value of a current, these intrinsic N's are considered as N is equal to 2 for a small rated currents and N is equal to 1 for a large rated currents. So this one I0 for a silicon diode, it is given as this expression. This is experimentally readings are to be found by the scientists. Okay. Next, what are the terminal characteristics associated with the PN junction diode? So the terminal characteristics associated with the PN junction diode. So let's see if we consider the VI characteristic of a PN junction diode. So this VI characteristic is divided into the three distinct regions. One is a forward, second is a reverse, and third is a breakdown region. So to this one, we need to define, yes, it's a what will be their behavior under the forward bias current. When the diode is a forward bias current, we have found out a diode equation which is given as I is equal to I naught, yes, reverse saturation current into e raised to V divided by intrinsic NVT minus 1. So this one where is the saturation current, yes. Now what is this one? This one is a temperature dependent component. This can be also written as this expression I naught. It can be written as it depends on the area of the material, cross-sectional area of the material. So if we say that if this area is a double, definitely reverse saturation current will be also double. And if this reverse saturation current is a double, then there definitely the current flowing through a diode under the forward bias is also double. So therefore, this I0 is also called as a scale current is also there, or it's a saturation current is also there. So it can be seen that through the depends on it's a diode current depends on what the saturation current I0 is, which is approximately double for every 5-degree rise in the temperature. How that we will take a discussion in subsequent slides. Then area of the material, yes, and the intrinsic N depending on the materials and the physical structure will be there. Now for appreciable current in the forward bias, it is assumed that yes, I is very greater than I0. Yes. So finally we will have this expression I is approximately, since if you consider that this expression guys, I will take it this one. We observe that for this value is a large as compared with 1. So this expression can be approximately written as a I0 reverse saturation current into this exponential term, which is represented as for appreciable current in the forward bias direction, forward bias configuration, forward direction current is given as like this way. So we have this will be approximate appreciable current. So it can be represented as in the logarithm form. Taking log to the base e, you will have log to the base e, yes, is equal to this expression. If we slightly rearrange this one, you will have this expression. So from this expression, what is your observation? If you observe that, yes, this is your applied potential externally. to the PN junction diode under the forward bias condition. It depends on what is the value of a VT, which type of a material is used, and it depends on the scale factor of a diode current and the reverse saturation. So from this discussion, we can see that for let one current and the second current I1 and I2, for that current, what should be the V1 and V2 respectively we need to find. And for that purpose, we will represent for I1 and I2. Yes, we have these two expressions. If we want to take a ratio of these two, let I2 will be divided by I1. So finally, we have this expression. Yes, I2 divided by I1 is equal to this term divided by this. So I0 gets cancelled. This term divided by this exponential term divided by this exponential term, and the exponentially divisions leads to the exponentially subtraction. So with a constant term we are taking NVT is a common. So you will have e raised to V2 minus V1 divided by NVT. So finally we want to find out what is the potential difference between these two. For that purpose, we will take it's a logarithmic on the potential. So by taking a logarithmic, you will have NVT log E, yes, I2 divided by I1. So this is a logarithmic to the base E. So this logarithmic to the base E can be converted into the logarithmic to the base 10 by the relation between logarithmic E to the logarithmic 10, which is a factor is a 2.3. So from this expression, it is a depend that the voltage difference or there is a voltage is a change by a factor, yes, 2.3 N into Vt. Now if we consider that what type of a material, either silicon material or the germanium material, for the germanium material this N will be 1. Yes, for the silicon material, this intrinsic N will be a what type of a current. For small current, it will be 2. For the large current, it will be 1. So, it will be. So, if you observe that guys here, this is a log to the base 10 to the I2 divided by I1. Yes, so this is a voltage and this is a current. So, you can plot here voltage and the current versus a characteristic which in the logarithmic scale. Yes. So the above equation gives for the decade value of a factor of a 10. The change in a diode current, the diode voltage drop change by a 2.8 intrinsic in VT, which is a 60 millivolt for intrinsic N and 120 millivolt for intrinsic N is equal to 2. So what is here? VT is what? At a room temperature, VT is given as a 26 millivolt. Yes, guys, or it will be a 26 into the 23. So 2.3, you will have this value. So as it is a logarithmic scale, it can be plotted on a semi-log paper. Now next, what about the reverse bias configuration? Reverse bias, this was the region up to this vertical line. It's a reverse bias. When the diode is a reverse bias, its a current is equation is given as yes, I is equal to I0 e raised to under the reverse bias. This is a negative sign, guys. This voltage applied externally is a negative because we are connecting a positive terminal of a battery to the N side and negative terminal of a battery to the P side. So we are applying a reverse voltage. So it will be reverse voltage. And for that case, what will be that? This value. This value is a very small. Yes. So when we consider that, if we consider that applied potential is a very greater than the 26 millivolt under the at the room temperature, then this expression is approximately sorry, this expression, this value is very small as compared with 1. So this expression is approximately 1. So finally we can have under the reverse bias region, the current is approximately reverse saturation current. Yes, I naught. So It's a I naught. The large component of a reverse saturation is here it is a due to the leakage effect. These leakage current are proportional to the junction area just as I0. By thumb rule, it is a 10 degrees Celsius rise in a temperature. These discussions we will take in a temperature effect of a diode or effect of a temperature on a diode. At that time, we will find why it is a rise for 10 degree, double for every 10-degree rise in temperature. This discussion we will. Now, lastly, breakdown region. This is the breakdown region. Here it is the breakdown region. Okay. So, what we'll have? So, the breakdown region is entered when the magnitude of the reverse voltage exceed the threshold value. That is specific to diode, which is called as a breakdown. And this is represented also called as the knee voltage. The voltage at the knee of a VI characteristic was denoted by the V subscript Z. Z stands for zener and K stands for guys knee voltage. So it's mostly represented as a VZ. Now guys, we want to solve the numericals based on the diode equations. What is the diode equation? Diode equation generalized, it's given as a either it's a silicon material or the germanium material. So guys, I request all the guys, you have to unmute from your end. Unmute from your end guys and speak with. Now we will have a discussion about the numericals. Yes, the first numericals as the, please reply me guys. Hello. Yes. Let's. Arya, you have the first question. Okay. Arya, the current flowing through the silicon diode at a room temperature is 9 into 10 raised to minus 7 ampere. When a large reverse saturation voltage is applied, calculate current through diode when 0.4 volt forward bias is applied. Consider that intrinsic N is equal to 2. Now, what is the information provided here, guys? First, if we read the problem carefully, yes, what is the problem information provided you? Read the problem carefully. The current flowing through a silicon diode at a room temperature is current flowing through at a room temperature is 9 into 10 raised to 10 raised to minus 7 when a large reverse voltage is applied. Large reverse voltage is applied means what? You will have a reverse saturation current for this case. So you will have the I naught. So I naught is equal to 9 into 10 raised to minus 7 ampere. Now calculate the current through the diode. So we need to find I when 0.4 volt forward bias is applied. So what is the V? V will be a 0.4 volt and the intrinsic N is equal to 2. Yes, for this case you have this value 9 into 10 raised to minus 7 which is a reverse saturation voltage I naught. Okay, V given 0.4 volt, intrinsic N given 2. Yes, and they have suggested that at a room temperature, what is the VT? VT is given as a, yes guys, T divided by 11600. And at a room temperature means 27 degrees Celsius. At a room temperature, T is a 300. So if you find out